for fun. So supply and demand are constantly shifting because of the 5 factors that affect supply and the 5 factors that affect demand. Because we can never control those things, we get this mess. And kind of in the textbook, we can identify, we can see the supply curve and we can see the demand curve. So if I asked you, where does supply 1 and demand 0 intersect, we can find that. Where does supply 1 and demand 0, and so we can find all these combinations. But we don't get to see these curves. What we see is the data. What we see is that. And from this, we have to try to estimate usually demand curves, but also supply curves. So again, think about this as just being a data set. It's a data set with 4 points. It could be 4 million points, it could be 4,000 points. We're just going to simplify this with 4 points. The definition of regression is it's the line that minimizes the sum of the squared distances from all the observations. So basically, it's a line that best fits the data. So that's what OLS does. That's what ordinary least squares regression does. That's what we've been doing in this class and in 580. So we're going to try to find the line that best fits the data. Is that a line that best fits the data? Sure. It kind of minimizes the distance of any single, so no single point is further away from the demand curve than any other single point. So that's not a bad estimate of a demand curve. But it's not the only estimate either. How about that one? Could that be a demand curve? Sure. Look at it. We've got 0 deviations for 2 points, and for the other 2 points, we're going to have some distance from there. But that demand curve 1, could just as plausibly be the correct demand curve as demand curve 0. What about that one? That one could be a supply curve. That one could be a supply curve. The point is we don't know. So when we run our regression, when we type reg whatever, even if we've accounted for all these things, sometimes we'll get wacky results. Sometimes we'll get a positive price coefficient, for example. And what we may be doing is accidentally estimating a supply curve instead of a demand curve. Or vice versa. Sometimes when we estimate a supply curve, we get a negative coefficient and we're estimating a demand curve by accident. So this is called the identification problem. We can't identify which one of those is the correct curve, right? We saw how they were all, by the way, none of those are correct. Every one of those is wrong, but they're all plausible mathematically. Remember that each one of those points reflects an intersection between supply and demand. It's an equilibrium point. So when we observe a price, that's the interaction between supply and demand in the market working. When we take that data, those observed prices and quantities, and we try to estimate a demand curve or a supply curve, then we're kind of stuck in this situation. Which one is the right one? We don't know which one is right. In this case, every one of them is wrong, but we don't know which one is the least wrong, for example. And we have no control over which one we get. The mathematical process that regression runs is just going to simply answer that question. Find me the line that best fits the data. And any one of those could be a plausible result from our regression. So this is the identification problem. We can't identify supply from demand, and even among alternative demand curves, we can't identify the right one. So what do? Well, what we can do is just through our understanding of supply and demand. Does that make sense? That that's a problem? Right? again, this one could be this could be a real elastic demand curve. So, but what we can do is kind of take our knowledge of kind of simple economics and say something along the lines of this. What if we added one of our factors that affect supply, one of those shifters of the supply curve to the supply equation? So let's add input prices. Now we can specifically control those shifts in the supply curve. What that allows us to do is say, look, when input prices change, and these are called instruments, but we'll get to that in a bit. As the supply curve shifts, either back or forward, up or down, it's going to allow us to do what? It's going to allow us to trace out the demand curve, to identify these 3 points as points along a demand curve, because we've specifically accounted for factors that shift the supply curve, and hence now we can what's called identify that demand curve. So the identification problem is solved if we can shift the supply curve and trace out a demand curve. That's literally what we're doing.
So you use supply shifters to identify demand.
Exactly. So that's the key. We gotta understand those factors. That's why we went over that. We gotta understand those factors that affect the supply curve, so that we can use those to identify the demand curve. Usually, the most obvious one is input prices. Input prices are usually pretty obvious to use as an instrument to identify the demand curve. But it's got to be, again, it's got to be something in the supply curve that's going to shift that supply curve up and down so that we can trace out or identify that demand curve. All right, and these are the 5 factors we already talked about. So technology is going to be hard. Price of inputs, probably the most common one. Price of related goods in production, sure. These are those complements and substitutes in production, the price of those things. Number of suppliers might make sense too. As you get more competition, that's going to shift that supply curve out there also, and we'll be able to use that. Expected future price, again, that one's kind of iffy, but just kind of knowledge of these factors is going to help us trace out that demand curve, which is what we need to do. Otherwise, we can get stuck with one of those other demand curves that were literally all over the place. Okay. Now, let's add income to the demand equation, because that seems like an obvious choice. So, if we wanted to identify the supply equation, then we would have to shift the demand curve. So we need something in the demand curve, we need to include into our model, something in the demand curve that shifts it up and down so that we can trace out the supply curve. So now we can, again, shift the demand curve and literally trace out that supply curve, and then be confident that when we run our regression, that we're actually getting a supply curve and not by accident a demand curve, or by accident one of those other curves that were flat or perfectly vertical or all over the place. Estimating demand, estimating supply, again, this is just endemic. It's always in what we're doing. Okay, so any factor in the demand curve that doesn't appear in the supply function will serve as an instrument. And that's going to include, actually expected future price shouldn't be there because that's in both the supply and demand function. All right. So here's our simple model of supply and demand, which we had earlier. Here's another way to look at the problem. Price, we usually consider price exogenous. In other words, we change price, or we observe changes in price, and then we see how it affects how much we buy. For example, if we're analyzing demand. And that's literally what we're doing. Right? When we do this, and remember the axes are reversed. So price per unit, quantity, here's a demand curve. And normally we get, pretty nice scatter, but we can see that, when price is high, people tend to buy less, and when price is low, people tend to buy more. In other words, price is outside of us, outside of us, the consumers. It's outside of our control, and it dictates how much we buy. So price is considered exogenous. It's generally considered exogenous. But it's not. We know that price and quantity are both determined simultaneously by the interaction of supply and demand. So price really isn't endogenous because it's determined inside of the model. And we know that each price and quantity pair represents a separate equilibrium condition in supply and demand. So even though we treat price as exogenous, it's really not. It's not exogenous. It's determined within the model. We just finished saying that price is determined by the interaction of supply and demand, so it's not determined outside of the model and kind of thrown in there. It's actually part of the equilibrium process. And this is the problem of, these are kind of technical, but if price is not exogenous, what's the opposite of exogenous? That was that other term in the first slide of the PowerPoint. It's endogenous. It's determined within the model. So it's not exogenous, like it's supposed to be. The entire regression process is based on the fact that our independent variables are exogenous and they exert influence on our dependent variables. So if you think of things like, think about something that's purely exogenous. If you think about natural experiments like how do you spell height? Is it H-E-I? No, I-E. It's one of those. It's H-E-I. No, I before you. Yeah, yeah.
English is
except,
awesome.
yeah.
I before you.
Except
in height.
when it sounds like an A, but that doesn't sound like an A. So, this is, so think about height of a flower, of a plant, and sun, right? Sun determines whether the plant grows big and tall. So sun is truly exogenous because the height of the flower has no control over the sun. But that's not necessarily true of price, because we know that price will affect both supply and demand, and that will again affect our, so let's draw that over here. So why is price not endogenous? I'm sorry, why is price not exogenous? Okay, so let's say that something truly exogenous occurs. Like a fire happens. It wipes out a bunch of the supply of houses. So the supply of houses shifts back, and both price and quantity get affected. So price doesn't operate independently, it's not exogenous. It's determined within the model by the interaction of supply and demand. So when supply shifts, it's going to affect both price and quantity. So it's not just a one-way causality. And that's what we're saying here. Price is not exogenous like sun, it's endogenous. Or think of this as sun or fertilizer. Right? You did this in biology, right? You got a plant and you put some fertilizer in one and a little bit more in another. I remember doing that in biology in high school, I think. And we tried to see what happened to the plant. And those are controlled experiments. The amount of fertilizer is literally controlled by us, the experimenter, and it's purely exogenous to the height of the plant. So that's an exogenous variable. Price, unfortunately, isn't, because price isn't determined outside of the model, it's determined by the interaction of supply and demand. So let's kind of get to this. This violates one of our ordinary least squares assumptions, which is that the error is independent of, that's what this means. The error is independent of the independent variables. We're supposed to have that assumption. But as we said here, if we treat this as demand equals beta 0 plus beta 1 price plus u, and supply is alpha 0 plus alpha 1 price plus u, right? When the error term, let's say that there's the error term, there's a shock to the error term, and it shifts us back here. And now the error term shifts supply and both price and quantity changes. What that means, and x is supposed to be price. What that means is that our error term is not independent of our independent variables. It's supposed to be. If it's not, then we end up violating this zero conditional mean assumption for our error. That means our estimates, our beta coefficients, are going to be biased, means they're going to be consistently either high or low. And they're going to be inconsistent, meaning that as we get more data, as our sample size increases, it doesn't, the bias doesn't disappear. A lot of times larger data sets will kind of eliminate some problems, but in the case of endogeneity, it doesn't get any better as the data set gets any better. We're still stuck with the problem. All right. Sales and advertising. Another one of those examples that we do. Again, normally what we like to think of, let's go through, let's burn through this real quick. Total revenue minus total cost. Don't worry about all this, this is just all derivation. Here's some calculus, here's some cool stuff, here's some more cool stuff.
It's cool when it goes by fast.
Yeah, it's like a bad dream. So, from our profit maximization problem, we get some interesting results. And it's these results here. And the result is that the ratio of advertising expenditures to total revenue, how much we spend on advertising, is dependent on advertising elasticity and the price elasticity. And that this is actually a profit maximizing condition. We should continue to advertise until this condition holds, until our advertising elasticity and price elasticity ratio is equal to our advertising expenditure to total revenues ratio. What all this means is that advertising really isn't exogenous. What this tells us is that for firms that are following kind of an optimal advertising rule, it means they're going to consistently advertise the expenditures on advertising expenditures are going to be some consistent percentage of sales. And we can see that by just rearranging this. So if we take that, right? So advertising expenditures is A times T, which is advertising times the cost of advertising. It should be P times total revenue, P times Q. In other words, optimal advertising should be some ratio of total revenue. In other words, advertising isn't strictly exogenous. There's a rule for advertising, and this is the rule that you should follow. And it comes from this profit maximizing problem that we can derive using calculus and all that kind of good stuff. So you have to take my word for it. So advertising is not endogenous, not endogenous. No, advertising is endogenous. So what does that mean? It means that we want to measure the effect of advertising on sales. But we also know if we're following the optimal advertising rule, which I rewrote over there on the board, if we're following the optimum advertising rule, then if advertising increases sales, and as sales increase, what should we do? As sales increase, what should we do? What is this rule tell us? As sales revenue increases, as this increases, what should we do? Increase advertising, right? So it means that we have this feedback loop. The more we sell, the more we should advertise. So this is that. So we had three terms up there. We had endogeneity, identification, and this is called two-way causality. Yes, we're trying to measure the effect of advertising, but we're also going to confuse that and muddle that with the effect of increasing sales on our advertising expenditures. So how do we isolate those? We're going to have to use these. These are all the same problems. They're all endogeneity and identification problems. Yeah, two-way causality. Let's see. We can introduce, let's ignore that. So here's our advertising function. And again, what we have is kind of a supply and demand model. So we have our sales function. Move beyond supply and demand. It's just another example. So we've got our sales function. So we got sales equals beta 0 plus beta 1 advertising plus our error term UI. So our sales function. So we're going to try to think this through kind of like the supply and demand equation. So we're going to construct now an advertising equation. Advertising is going to depend on sales. Oops. And we know that from the feedback loop. But also advertising is going to depend on, what am I calling price of advertising. So remember what we did to identify a demand curve. We needed something that shifts the supply curve, but doesn't affect the demand curve. And we use that to trace out the demand curve, right? We shift that supply curve, trace out the demand curve. We're doing the same thing here. We need something that affects advertising, but doesn't directly affect sales, so that we can identify our sales function and get a better measure of our advertising coefficient. That shifter is going to be the price of advertising. The price of advertising is our instrument. It's correlated with advertising. Clearly, as the price of advertising increases, we'll buy less advertising. As it decreases, we'll buy more advertising. So they're clearly correlated. And the price of advertising is uncorrelated with the error term, which is just a fancy way of saying the price of advertising doesn't belong here. Advertising does. And the price of advertising affects advertising, but it doesn't affect sales directly. It's an indirect effect through the advertising equation. Does that make sense? It's pretty complicated. Like I said, this is really technical stuff. But like I said, it's endemic. And it's something you really have to deal with on a daily basis when you're doing analytics, at least the kind of analytics we're doing. Whenever you're running regression, you really have to ask yourself, is there an endogeneity problem? If so, how can I fix it? How can I measure it? And do all those kinds of things. All right, we'll try to formalize this. All right, so there we go. Two-way causality, yeah, we got that. Yeah, same thing with creating problems. Yeah, biased and consistent. Okay, nature of simultaneity. Let's see, don't worry about all this stuff. Essentially what this boils down to is, yeah, we got this simultaneity, identification, two-way causality, we got all that stuff. We know our results are going to be biased, but we can at least predict the direction of bias. So if our endogenous variable in U, so let's go back to supply and demand. Price plus U. So U is our error term in the equation that we're most concerned with. Price is our endogenous variable. It's not strictly exogenous. Okay. So if our endogenous variable and the error term are uncorrelated, if it's truly exogenous, then we have an unbiased coefficient on price. If they're positively correlated, then there's going to be positive bias. If they're negatively correlated, there's going to be negative bias. So what does that mean? It means that if the error term increases, so we can see that, and we can literally see that. And beta 0 plus beta 1. Price plus U. Alpha 0 plus price plus epsilon. So we want to see how the error term and our endogenous variable are correlated. What happens? So let's increase the error term. And an increase in the error term is going to shift out our equation, right? It's just a constant, so it's a shifter. It's going to shift out our equation like that. So when the error term increases, what happens to price? It increases also, right? So the error term, which shifted the demand curve, and price are positively correlated, which means we're going to get positive bias in our coefficients. When we run this regression, our effective price is going to appear bigger than it really should be. If these were negatively correlated, we get the opposite direction, opposite effect. All right. Luckily, there's a test for endogeneity. All right, so suppose x1 is endogenous. Let's construct a equation for x1, factors that affect x1. So we're saying that x1 is endogenous, so x depends on y, and it also depends on some other variable called z. Z is ultimately going to be our instrument that we're going to use to identify y. All right. These are called structural equations. Okay. We're going to use something called the Houseman test. Houseman test is pretty simple. All right. So step one, take the endogenous variable and use it as the dependent variable with all the exogenous variables from every equation. So take the problem variable, which is x1, and run it against everything on the right-hand side of all the other variables. Notice y is not up there. So x2 is up there and z is up there. Take that. This is called a reduced form equation. There's a bunch of math that goes involved with this. And save the error term. So run that regression, save the error term. Let's call that squiggly hat. So here's the error term, there's squiggly hat. Then we're going to take squiggly hat, and we're just going to throw it into our equation of interest. So here's our equation for y, right? So here's x1, here's x2, and there's squiggly hat.